Hello everyone. In this video, we are going to be completing a quiz review for the quiz on complex numbers. So essentially, we're going to go over all of the skills that we have learned since we started going over imaginary/complex numbers. Here is a list of all the different skills that are being assessed on the quiz because they're the skills that we've learned so far. So the first thing we learned is about simplifying negative radicals. And that's because it's a negative radical. That means you're going to have a solution with I in it. Then we went over solving quadratics with complex solutions. So using the square root method, and again, your answers having I in it. And then more recently, we talked about evaluating the powers of I, which will be on the quiz, as well as operations of complex numbers, operations being addition, subtraction, multiplication, and division. So we are going to go through all four of those different things just in order throughout the process of this video. So here we are starting with simplifying negative square roots, okay? And before we even start that, we should have a quick reminder of what exactly is I. Okay, and I is the square root of -1. Okay, and that's sort of the basis for everything that we are doing in this video and everything we've been doing in this unit. So you should know that by now. If you don't, again, it should be somewhere in your notes in really, really big font, circled, starred, underlined, bolded, whatever you do to make sure you remember something and never forget it. That's the foundation of all of this. So you're looking here, if you look at number 1, for instance, we have the square root of -25. Now, if there was no negative there, you could take the square root of 25 and your answer would be 5. You'd be good to go. But there's a negative under that square root sign, and your whole life you've learned that you can't take the square root of a negative number. And that's because the square root of a negative number is not a real number. If you type the square root of -25 into your calculator, it will tell you there are no real solutions or something along those lines. It'll give you an error message. So what we have to do is we have to express this as an imaginary number in order to simplify it. And what that means is basically factoring out the square root of -1. And once you get rid of that negative, you can take the square root like you would any other time. So what I'm going to do is I'm going to rewrite this radical, and instead of writing it as the square root of 25, or square root of -25, I'm going to write it as the square root of 25 times -1. Okay, and what I've done here is I've rewritten it so that the negative is separate from the positive portion, okay? -1 times 25 is -25, so those two are equivalent, but I've written it in a new way. And now I'm going to go even further, and I'm going to separate this into two separate radicals. You don't necessarily need to write this, but sometimes it helps us to see this visually, okay? And once I break it up into two separate radicals like this, it makes it easier to simplify because I have two pieces. The first piece is the square root of 25. Now, we should know our squares at this point by memory. If you don't, that's something you should work on. But the square root of 25 is 5. Again, worst comes to worst, I guess you can type it in a calculator, but you really should know these first at least 12 perfect squares by memory. So the square root of 25 is 5. And then you have the square root of -1. Oh, the square root of -1. I know something that represents the square root of -1, and that is I. So instead of writing the square root of -1, I can replace that with I, since the square root of -1 is I. And so simplifying the square root of -25 gives you 5i. And then I'm going to do the same thing with these next couple numbers. So I have the square root of 121, and I'm going to separate this right away into the two radicals like this. I don't think I need to write this twice. But again, -1 times 121 is -121, so I haven't changed the value at all. But this allows me to take the square root of 121, which is 11, and then I can replace the square root of negative with I, square root of -1 with I, since that is what I is equal to. And this gives me 11i. Okay, now if you notice something, basically what's happening when I have the negative root is that when I simplify it, I just have what the normal square root would be, but then I have an I at the end. And that's because I will always just end up representing the negative portion of this root. So if you have something like this, say the square root of -64, I know that this is just going to be the square root of 64 times I, because you're pulling the negative out and the negative becomes I. So I can just go straight to this because I know the square root of 64 is 8. Okay, but if it helps you, or it's at least nice to go back and double check, right? I can break negative 64 into positive 64 and negative 1, and then you'll see how root 64 becomes 8 and how root negative 1 becomes I. Okay, so now we have some more examples, but you might notice looking at these that none of these are perfect squares, so there's going to be one other step. So we still have to do that first step where we bring the negative out and we make that basically I. So I'm going to do this like I showed you on the last problem, and I basically skip to just bringing this I out there because I know the I represents the square root of negative 1. And from here, I'm going to have to simplify my radical. It doesn't come out as a perfect whole number, so when we say simplify, we mean find two factors where one is a perfect square, and we are specifically looking for the greatest perfect square. So if you make a list of perfect squares, right, for instance, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, etc. Your list of perfect squares is basically going to be this. Oh no. My screen never writes that well when I do these videos. Maybe I'll separate them by commas so they're easier to see. Right? But again, I said we should have our perfect squares memorized by now. Here are the first 10 perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Okay? So basically, I'm looking for what are two factors of 27, right? So two numbers that multiply to 27, but I want one of them to be the largest perfect square factor, which means of that list of numbers that I just wrote down here, what is the largest number out of that list that factors into 27? Or in other words, that 27 is divisible by. Obviously, you can't divide 27 by like those really big numbers such as 100 or 81 because they're literally bigger than 27. But I can look at the numbers smaller than 27 and see what is divisible by. Now, you're going to want to start with the biggest number you think could possibly it could be divisible by, which is always going to be a number smaller than 27. So I'm going to start around here and think, well, can't divide it by 25, can't divide it by 16. Oh, 27 is divisible by 9, right? So I like to work from the larger numbers towards the smaller numbers, but then the first number you come across that 27 is divisible by is going to be the number you want, right? Because I started with the bigger numbers. And again, you're looking for the largest perfect square factor. So what I can do now is I break 27 into two numbers. So I know 27 is divisible by 9, but if I divide 27 by 9, I get 3, right? And so the product of 9 and 3 gives us 27. Okay, so I'm breaking root 27 into root 9 times root 3. Okay, and then again, just like what we did with the imaginary numbers on the last slide, I'm going to break those into two separate radicals just because that allows us to evaluate each separately. The square root of 9 is 3. The square root of 3 cannot be simplified any further. That would just come out to a decimal, so I'm actually going to leave that as just root 3. And that gives us our final answer of 3 root 3i. Now let's move on to the next one. Again, first step here is I'm going to separate this into the real and imaginary part. So root 128 times I. Okay, again, that negative part of the square root becomes I. And then I need to find the largest perfect square factor of 128. Okay, so basically 128. Can I divide it by 100? Doesn't work. Can I divide it by 81? Doesn't work. Can I divide it by 64? Oh, yes, I can divide 128 by 64, and that would give me an answer of 2. So I'm going to rewrite this as 64 times 2. Okay. Now, this is why I suggest you start from largest to smallest, because if you start with the smaller numbers, you're going to find that 128 is divisible by 4. And maybe you'll even keep going and be like, oh, it's also divisible by 16, so I'm going to divide it by 16. But you, in that case, wouldn't have the largest perfect square factor, so you wouldn't be totally simplified. So again, I just start with the larger perfect squares in order to avoid that whole problem. Okay. So from here, again, I have root 64 and root 2. You could rewrite it like I did over here. You don't necessarily have to write out this step. Right now I'm seeing that I have a 64 under the square root symbol, and I can pull the 64 outside the square root symbol by actually taking the square root, and I can simplify the square root of 64 to 8, whereas I can't take the square root of 2, so, or, it would become a decimal, and I don't want decimals, I want to simplify. So I'm going to just leave that as the square root of 2, and it becomes 8 times the square root of 2i. Again, if you wanted to write it like this step over here that I had put the star next to, in between these two steps, you could break those into two separate radicals, right? And that might help you if you're kind of struggling with this, just to see it really step by step, and then square root of 64 becomes 8. Okay, but I'm just sort of skipping that step to show that you can, for anyone who is at the part where that's what they want to do. Now, I'd like you guys to try number 6. If you're watching, I think you should pause this video, try it on your own. That's the best way to study, is to make sure you practice on your own. And then once you finish doing that, you can come back and watch me explain it. Okay. So in order to find the square root of negative 75, again, I need to break it into the real and imaginary parts. The negative root becomes just an I. When it comes to finding the square root of 75, again, not a perfect square, so I'm going to need to find the largest perfect square factor. So I'm looking for numbers smaller than 75. What could I divide 75 by? Well, I can't divide 75 by 64. I can't divide it by 49. I can't divide it by 36. Oh, when I try dividing 75 by 25, I finally get a whole answer. So since 75 is divisible by 25, I rewrite this as the product of 25 and 3. Okay, again, the reason I can do that is because 25 times 3 is 75. Okay, it's just written in a different version. Okay. And then now I'm splitting it into two radicals. Again, this step you can skip if you want to, but if it helps you visualize, make sense of it, then you can keep doing it. The square root of 25 is 5. The square root of 3 cannot be simplified, and the I is just along for the ride, which leaves us with an answer of 5 root 3i. Okay, so now that we've covered simplifying radicals, what we are doing now is we are going to start solving. So here we have a quadratic equation. Okay, remember quadratic just means I have a squared variable. So I have x squared equals negative 25. Now to solve this by the square root method, I need to get x by itself by taking the square root of both sides, right? And I do that because the square root and the square are opposites of each other. So I'll take the square root of both sides. Now there's two things to remember here. The first thing we have to remember is whenever I take the square root of two sides of an equation, you have to do plus or minus whatever your answer is. The reason we have to do that, okay, is because when you square something, like a negative squared is a positive, right? So the same term, whether it's positive or negative, when you square it, it comes back out the same. So anytime you're solving and you take the square root of both sides, you have to put plus or minus. Okay, so that's a really common mistake, is to forget that. Please don't forget it. Okay, and then I have plus or minus, and then just square root of negative 25. Okay, and then again, please, as soon as you're solving, don't just forget how to simplify a negative radical. Okay, remember that the square root of 25 is not just negative 5, because you can't actually take the square root of a negative. That's not how it works. Okay, if you take the square root of a negative, you don't get a real answer. So we have to break this apart, just like those examples we did earlier, where I turn this into an imaginary number. Right? Technically already is imaginary, but I'm going to write it with I. Okay, so the plus or minus just sort of comes along for the ride. The square root of 25, square root of negative 25, again, I split it into the real and the imaginary part. So since the square root of negative 1 is I just have to bring that I out, and that accounts for that negative that had been there originally, because I is just acting as the square root of negative 1. And then the square root of 25 comes out to 5, so I can simplify that part, and I find that my final answer is that x is equal to plus or minus 5i. Moving on to the next example, it's just one that's a little bit more complicated. It's going to be more than that one step. So here again, I have another quadratic, 3x squared plus 144 equals 0. Okay, so I'm going to have to solve. Please bear in mind the order that you have to solve in. We work through the reverse order of operations, in other words, the opposite of PEMDAS. So you would start with any addition or subtraction, then move to multiplication or addition, and then deal with the exponent. Okay, the other way to think of it is I have to start by isolating the squared term, and so I'm going to have to remove this plus 144 first. Okay, so I'm going to start by subtracting 144 from both sides. And when I do that, cancels on the left, that leaves me with 3x squared is equal to negative 145. Okay. Now at this point, some people tend to make a mistake. I'm not sure why this is such a common mistake, but some people at this point will try to take the square root of both sides. I guess it's because they don't see a whole other term. Okay, but you cannot take the square root yet because your x squared, it's still not alone, right? That 3 there, the 3 is not being squared, okay? An exponent only refers to the immediately preceding term unless this stuff is in parentheses. So the only thing being squared is the x, so I can't take the square root until everything on that left side is being squared. So I have this plain old 3 that's hanging out there, and I have to get rid of it first. Since it's now being multiplied, I'm going to divide it to move it to the other side. Okay, here I have to take negative 145 and divide it by 3, which gives me negative 48. And at this point, now I have my squared term isolated. The left is x squared, the right is negative 48. So I can go ahead and take the square root of both sides in order to isolate the variable. Okay, because square and square root are opposites, those cancel, and I'm left with just x on the left side. On the right side, again, I have plus or minus the square root of negative 48. Okay, or in other words, the square root of 48i, right? I pull that negative out, it's the imaginary part, it becomes I. Okay. Now at this point, I'm looking at what is the square root of 48, and that's not actually a whole number, so I'm going to have to go ahead and simplify that radical. Okay, so I'm looking for the largest perfect square factor that fits into 48, and this is where it comes in real handy to have all those perfect squares memorized. If you don't have them memorized, I'd multiply them all out and keep yourself a list handy. Okay, but the next largest perfect square, the one that's right smaller than 48, would be 36. It's not divisible by 36. The next smallest is 25. It's not divisible by 25. The one smaller than that would be 16. And 48 is, in fact, divisible by 16. If you divide 48 by 16, you would get 3. So I rewrite this as plus or minus root 16 times 3i. And then again, I'm taking the square root of 16 and the square root of 3 separately. The square root of 16 is 4. The square root of 3 cannot be simplified, so I just write it as root 3 still. And the I comes along for the ride. This gives me my final answer of x is equal to plus or minus 4 times the square root of 3i. Okay, now we have a similar problem, but it's worded different. So it's asking me to find the solution of the following equation. So this is in function notation, f of x equals 2x squared plus 98. It asks for the solution. This goes back a little bit, but if you remember, we talk about solutions. A solution is also called a root. It's also called a zero. Okay, and so basically the solution is where the function is equal to 0. So I actually, I accidentally clicked forward. In order to find the solution is where the function equals 0. So I replace f of x with 0, and then I'm going to solve from there. Okay. Now, once I've replaced f of x with 0, there's nothing different than the other problems. So from this point, I recommend that you guys get in some practice. So again, if I were you, I would pause this video and go ahead and try it on your own, and then come back for the solution. Actively doing the math, making mistakes, finding mistakes, correcting mistakes, that is how you learn, and that is how you will be best prepared for the quiz. Okay, so going over this, again, I'm working with the inverse order of operations. So I start with any addition or subtractions. So I'm going to subtract 98 from both sides. That leaves me with negative 98 equals 2x squared. Okay, because that canceled on the right side. Okay, again, before I take the square root, I have to completely isolate x squared. So I'm going to divide both sides by 2. That leaves me with negative 49 equals x squared. Okay. and then I'm going to go ahead and take the square root of both sides. Okay. And again, when I take the square root of both sides, the square root and square cancel, so I just have x on this side. Even though I've written out the negative 49, that's on the left side of the equation. Wherever your numerical expression is, so the number, that is what is going to be plus or minus. So I'm going to have to put the plus or minus the square root of negative 49, or in other words, the square root of 49i. And then all you have to do to find your final answer is take the square root of 49. The square root of 49 is 7. So I find that x is equal to plus or minus 7i. Again, you can always rewrite this if you want to, but the order you write it doesn't really matter. So, yeah. Okay. Last one of these type, again, I recommend that you go ahead and solve this out on your own first, and then I'm going to go over it. So pause the video. Okay, going over this, again, I'm asked to find the solution. The solution means where the function is 0. So I'm going to replace f of x with 0. Next, I'm going to subtract 60 from both sides. Leaves me with negative 60 equals 5x squared. I'm going to divide both sides by 5 to isolate x squared. That's going to give me negative 12 equals x squared. Okay. From this part, x squared is finally isolated, so I am going to go ahead and I'm going to take the square root of both sides, and I find that x equals plus or minus root 12i. Okay. Now again, I go to take the square root of 12 and I'm like, oh no, that's not a whole number. I'm going to have to simplify. So I'm thinking, what is the largest perfect square factor of 12? My perfect squares that are smaller than 12 are basically just 1, 4, and 9. Obviously, it's divisible by 1, but that doesn't help us. Okay, 12 is not divisible by 9, but it is divisible by 4. So I rewrite 12 as 4 times 3. Okay, which allows me to take the square root of 4, which comes out as 2. Once again, I cannot take the square root of 3, not a whole number. Okay, but in doing this, I find that my answer comes out to plus or minus 2 root 3i. It's supposed to be a 2, but it got really sloppy. Nothing new there. Okay, next thing we're going to talk about is powers of I. So this is stuff we did slightly more recently. Remember when we talked about this in class, we talked about how I is cyclical. Why am I getting an email at this time of night? That's kind of wild. But I is cyclical, which means that the value of I to different powers, it just sort of keeps coming back to the same numbers. So I to any power will give you I, negative 1, negative I, or 1. But basically you have to figure out where on this cycle your number falls. Okay, and just as we go about this, notice that the cycle itself, it has 4 possible outcomes, and every time you have an exponent, like you reach a multiple of 4, you start back at the beginning of the cycle, right? So once I get to I to the 4th, I'm back to the beginning of the cycle. When I get to I to the 8th, I would be back here. When I get to I to the 12th, I would be back there. So basically how we treat this is if you're given an exponent, let's say I to the 17, what you're going to do is take that exponent and divide it by 4. And what the whole number you're left with is going to tell you is how many cycles of 4 there have been. So how many times have I gone around this circle? And this indicates to me that I went around this circle 4 times. So 1, 2, 3, 4 times. Right now, at the end of 4 times, 4 full cycles, I'm here. But because there's 0.25 left, that's a quarter. I have to go a quarter more around the circle. And that is telling me that I to the 17 is equivalent to I to the 1st, which comes out with an answer of I. Okay. Now, you do not have to draw all those big circles I did every time. That is completely unnecessary because we don't actually care how many times I've gone around this cycle. All we care about is where on the cycle do you land. So again, that's why we go ahead and we divide by 4, because when I divide by 4, that takes away all of those times that have gone around a cycle, a perfect number of 4 times. And then what I really care about is this decimal here, right? Because I did 4 full cycles, don't care about that. I want to know after I've completed 4 full cycles, how much further do I have to go? Okay, and again, a full cycle, it ends at the top, I to the 4, that's the cycles of 4. And once I'm here, I have to go another quarter way around the circle, and my answer is I. So now we're going to go through a few examples. Again, if you already feel solid on this, I recommend you go ahead and already just go ahead and pause, solve these 4 out, see if you can get the answers, and then come back to double check. So feel free to pause now. Okay. And then going over these, again, what we're going to do is take the exponent and divide it by 4. So the first thing here is I'm going to be dividing 53 by 4. And when you do that, you get 13.25. Again, the 13 means I go 13 full times around this cycle from the beginning of it, from the top of it. I don't care how many times I go around it though. I care once I'm back at the beginning of it, I have to go 0.25 further, or in other words, a quarter of the way further. So I'm going down to here. That tells me that I to the 53 is equivalent to I to the first power, or in other words, that is I. The next thing we are doing is I to the 67th. So again, take the exponent, divide it by 4. When I divide 67 by 4, I get 16.75. Right? And what that indicates to me is that I went 16 full times around the cycle. But then again, starting at the beginning, which is the top, I have to go another 75% around the circle, right? 0.75 is 3/4. So I have to go 3/4 around the circle. And that tells me that I to the 67th is equivalent to I to the 3rd, which in other words is negative I. Okay. Now, I'm realizing at this point that I didn't go over why each of those, like in the original cycle, is true. We went over that in depth in class. So I'm going to sort of backtrack and talk about that now just in case. Now, I to the 1 is I because you don't need to write an exponent of 1. That's the same as not writing an exponent. It's sort of like we don't bother writing the coefficient of 1. When it comes to I squared, remember that I is the square root of negative 1. So if you square I, you have the square root of a square. And remember how the square root and square cancel each other. Okay? So if the square root and squared symbol are gone here, all I'm left with is negative 1. And that's why I squared equals negative 1. Okay? When it comes to finding I to the 3rd, what I'm going to do is I actually like to break this up. And instead of writing I to the 3rd, I'm going to write I squared times I, or in other words, times I to the 1. Right? I to the 3rd means I times I times I. Well, I squared is I times I, and then I have times another I here. So those are equivalent expressions. Both of them are 3 i's being multiplied times itself. But I already know from this last step that I squared is equal to negative 1. I just found that right here. Okay, so I can replace I squared with negative 1. I to the first power can't be simplified, but that leaves me with just negative 1i, or in other words, negative I. Okay, and that is why I to the 3rd is equal to negative I. All right, and then lastly, for I to the 4th, I to the 4th can be rewritten as I squared times I squared. Again, that's still a total of 4 i's. Each I squared can be replaced with a negative 1. And since negative 1 times negative 1 is positive 1, I to the 4th is equal to negative 1. Or sorry, is equal to positive 1. Okay, and that gives you all 4 of the values in the cycle of I. Okay. Now, as I said, because this is a cyclical function, as I increase in value, I'm going to keep working around this cycle. And that's because as I keep increasing from here, eventually I'll keep going back to that I to the fourth, because every 4, I'm going to get 1 since I to the 4 is 1. Right? So like if I want to know what I to the 5th is, I can simplify it to I to the 4 times I, right? And since I to the 4 is 1, a positive 1, it basically just goes away. And that's why I to the 5th is the same as I, right? For I to the 6, I could simplify that to I to the 4 times I squared, right? But again, I to the 4th is just a positive 1. I don't need to include a coefficient of positive 1, so that goes away. And that's why I to the 6 is the same as I squared, right? Which is why for I to the 6, you would have just kept moving around this cycle. Okay, so apologies if that was sort of a detour from what we were originally talking about, but I thought it was important I go over that for anyone who may have missed class that day or still didn't quite get that or didn't remember or, you know, whatever of the sort. Anyways, we are going to keep going now. We just have a couple more. Right, so my next problem here is I to the 90th. So again, because I works in cycles of 4, every 4th exponent brings me back to an answer of 1. I'm going to divide 90 by 4. Right? And basically I have 22 cycles around that I keep coming back to that answer of 1, but it's not just 22, it's 22.5. Okay, and so what that indicates to me, 5 is 0.5 is a half, right? So I'm back to the top of the cycle, but then I have to go 1/2 further. Okay, so I've gone 22.5 cycles. That would land me at the equivalent of I squared, which happens to be -1. Okay. And then the very last thing here is we have I to the 24th. So I'm going to divide 24 by 4, and that gives me an answer of 6. If you'll notice, there is no decimal there. That means that from the beginning, I take 4 full cycles, 4 complete cycles. I end here, and I don't have any further to go. So since this is a perfect multiple of 4, I to the 24 is equivalent to I to the 4. My solution, or my simplified version of this, is 1. All right, now we are finally at operations with complex numbers. This is our last topic. Of course, there are still 4 operations to go through, so we still have a little ways left in this video. We are going to start with addition. Now, if you remember in class, we talked about how you treat I like you would treat any other variable. So when it comes to adding complex numbers, what we're doing is we're just looking for like terms. Now, if you notice these parentheses here in these problems, there's nothing out in front of the parentheses, right? That's just blank. This is just an addition. So if there's no number out in front and no variable, no negative sign or anything out in front of the parentheses, there's nothing to distribute into those parentheses. The parentheses are really indicating nothing. They're just sort of separating that the first set of parentheses is one complex number and the second set of parentheses is another complex number. But mathematically, there's no difference between drawing in these parentheses or not. And again, that is because there is nothing outside the parentheses that can be multiplied or distributed into. So you can completely ignore the parentheses here and just start looking for like terms. So I see I have 2 constants, and then I have 2 imaginary terms. And I can go ahead and combine them. 4 plus 3 is 7. Okay. 2i plus 5i is 7i. And so my answer here is 7 plus 7i. Okay, and that works exactly like it would if those i's were x's. So there's not really anything new about this skill, other than we're doing it with I. Same thing with the next problem. This is again an addition. There's nothing outside those parentheses to distribute, so I just go ahead and start by looking for like terms. I have 3 and 1 are my 2 constants. I have positive 4i and minus 2i as my imaginary terms. 3 plus 1 is 4. And then positive 4i minus 2i is 2i, because 4 minus 2 is 2. So I'm left with 4 plus 2i. And just a note, we write all complex numbers in the form a plus bi. That happened naturally here because the parts we were given were written in a plus bi, but make sure that you always write your answers in this form. What that means, a is your real number, and bi is your coefficient, and then I. So just make sure that imaginary term always goes last and the real term goes first. Okay, here we're moving on to subtraction. So in the last couple problems, I told you that the parentheses weren't really indicating anything because there was nothing outside the parentheses to be distributed. That is no longer the case because there is a negative sign outside my second set of parentheses, right? So the first set of parentheses, there's really nothing happening there, right? 4 plus 2i is just sort of hanging out, so I can just go ahead and rewrite that. Okay, but there's a negative at the second set of parentheses that needs to be distributed to both terms within the parentheses. So the negative is distributed to the 3, and the negative is distributed to the 5i. Okay. Now, once I've done that, this is the same as that last step where I'm just combining like terms. So I'm going to find my constants. For instance, here, 4 and negative 3. I'm going to find my imaginary terms, 2i and minus 5i. Please, please, please remember to keep those signs in there. Okay, the sign does go with it. Okay, and then I can go ahead and combine those terms to get my answer. 4 minus 3 is 1. 2i minus 5i is negative 3i, right? 2 decreased by 5 is negative 3. Okay. Again, I like to see us doing this in our heads, sort of like the squares and the square roots. But if you tend to make mistakes when it comes to adding and subtracting negative integers, please double check that math in the calculator. While you might not be able to type your I, you certainly can type 2 minus 5, and your calculator will give you that answer of negative 3. Just like several other times in the video, I think this is a good time for you guys to try an example. So I'd like you guys to do number 2 on your own, pause the video, and then when you're done, come back to check your work. Okay, time to go over this. Once again, there's a negative for me to distribute, so I'm going to distribute the negative into that second set of parentheses. Since there's nothing to distribute to the first set, I just rewrite it. And then when I distribute the negative to the second set, I have a minus 1. And then I have a negative distributed to my minus 2i. Now, please be careful. When you distribute a negative, it does not mean you're going to be left with all negative terms. A negative negates, or it inverts, or it makes the opposite, whatever sign was already there, right? So since this was already negative, now I'm making a negative negative, right? A double negative is actually a positive, right? So remember, the negative flips whatever sign is there. So this original negative gets flipped to a positive, and I actually have plus 2i at this point. Okay. And once I've distributed it again, I'm looking for like terms. Negative 3, negative 1 are my constants. Positive 4i and positive 2i are my imaginary terms. So I have negative 3 minus 1. That is negative 4. Again, negative 3, I'm decreasing by 1, becomes negative 4. If you're having trouble with adding, subtracting negative integers, please double check in your calculator. Try it on your own first, but then just double check in the calculator. And then I have plus 4i plus 2i. So 4 plus 2 is 6. That leaves me with 6i. Okay. Here we are on to pure multiplication. So I see a term outside a set of parentheses. I'm going to distribute. 2i times 8. Well, 2 times 8 is 16. I comes along for the ride, 16i. 2i times negative 3i. Well, 2 times negative 3 is negative 6, right? We deal with the real parts. Now I'm going to multiply I times I. When something is multiplied times itself, you represent that with an exponent, so that leaves me I squared. From here, some of you might be thinking, yeah, I'm done. There's no like terms I don't have to combine. But it's also not in a plus bi form because I have an I term and an I squared form. Well, you are never going to need to have an exponent with the I because when I have these exponents, I can simplify them to at least I. Sometimes they simplify to real numbers, sometimes they simplify to I, negative I, etc. Okay, but they're always going to simplify any I with an exponent. In this case, I have I squared, and that's going to come up a lot. If you remember when we talked about the cycle of I, right? We said I is square root of negative 1. So I squared is the square root of negative 1 squared. Again, squares and square roots are opposites, so those cancel, those two symbols go away, and all it leaves me with is negative 1. So what that indicates to me is that I squared equals negative 1. So as soon as I see an I squared in my answer, I know this isn't actually my answer because I can still simplify this. There is no sense in writing I squared in my answer because I squared actually evaluates to a real number. So what I'm going to do is I'm actually going to rewrite this whole thing out again. But now I'm going to replace the I squared with a negative 1. Okay. Please be careful. It's I squared, so it's not the square root of negative 1. Okay. And it's also not a positive 1. I squared equals negative 1. So anytime I squared comes up, I replace it with a negative 1. Now, negative 6 times negative 1 is positive 6, so that leaves me with 16i plus 6. From there, there's nothing else to simplify because I have my real term, I have my imaginary term, can't combine further. But I will say we should go back and remember that we write our final answers in the form a plus bi, which means our real term, then our imaginary term. So I'm just going to rewrite this real quick by putting my real term first and my imaginary term second. And I get an answer of 6 plus 16i. Okay. Once again, pause the video, try number 2, and then come back and I'll go over it. Okay, so first things first, I'm going to distribute the negative I. Again, when I multiply and I have these coefficients or constants and I have a variable, I here sort of acts as a variable, even though it's technically not a variable, right? I'm going to start by just multiplying the real parts. So I'm multiplying negative times negative 2. And a negative times a negative is a positive, so that just leaves me with positive 2. And then I just have that one singular I, so that is 2i. Now, the next thing I'm doing is I'm distributing the negative I to the 10i. Here, the negative times positive 10 gives me negative 10. And I times I, again, something times itself is a squared. So that is I squared. Just like last time, my next step is to replace I squared with negative 1. Then I can go ahead and combine those two terms by multiplying, right? Negative 10 times negative 1 is positive 10. And then I'm writing it in the form a plus bi by putting my real term first. Before I move on, there is one thing I want to clarify, and I don't know that I have an example. Maybe it'll pop up in this video. But when I say I'm putting my real term first, let's say I had a totally different example. I'm just making this one up. Let's say I had 5i minus 7, and I wanted to switch this to the form a plus bi. Be very careful. The imaginary term is 5i, and the real term is negative 7, right? The sign always goes with the number directly after it. So since I have a negative 7, if I am to reorder this, this becomes negative 7 plus 5i. Okay, and I just wanted to be clear about saying that because a lot of people would be tempted to write 7 minus 5i. But again, that negative goes with the 7, right? It's locked in with the 7. So when you switch the order, the negative does have to go with the 7, and then you're still adding that positive 5i. Other than that, I think we're good with this slide though, so we'll keep on moving. Oh, we're so close to being done, guys. Okay, so here's some more multiplication. Here we're just multiplying binomials. So there's just 2 terms in each set of parentheses. So I have to do double distribution, not just single distribution. So I'm going to go with this, right? Distribute my first term to both terms in the second set of parentheses. 7 times 4 is 28. 7 times negative I is negative 7i. Okay, and then I'm going to be also distributing this I to the 2 terms in the second set of parentheses. So I times 4 gives me positive 4i. I times negative I, well, a positive and negative is a negative, and I times I is I squared. At this point, I have 4 terms, but I am noticing 2 of them are like terms. I have a negative 7i and a positive 4i. So I'm actually going to go ahead and combine those 2 together, leaving me with 28, and then negative 7 plus 4 is negative 3, so negative 3i minus I squared. As we talked about on the last slide, I squared is equal to negative 1, so I can rewrite this even further by saying minus negative 1. Again, please be careful. I squared is equal to negative 1, so that subtraction still needs to stay there. right? That is not being replaced. What I am replacing is just the I squared. So the minus sign is still there, and then I also have a negative 1. So I have minus negative 1, which in other words is plus 1. And then now we'll notice I actually all of a sudden have two like terms again. And that's what's going to happen when I simplify I squared and it becomes a real number, is I now have two constants that can be combined. So I have a 28 and I have a 1. So 28 plus 1 is 29. And negative 3i has nothing to be combined with. So my final answer is 29 minus 3i. So again, now it's your turn. Try number 4 and then come back for the answer. Okay. So as we are working through this problem, again, I'm going to do a double distribution. So I'm distributing 5 to 5 and 5 to 4i. 5 times 5 is 25. 5 times 4i is 20i. Now, I'm also going to have to distribute this negative 4i. Okay, please be careful if that set of parentheses has a minus sign that indicates that second term is negative. Okay, so you're distributing the entire term, which includes the negative. So I'm distributing a negative 4i to both 5 and positive 4i. Negative 4i times 5, well, negative 4 times 5 is negative 20, so that leaves me with negative 20i. And then negative 4 times 4 is negative 16, and then I times I is I squared. Okay. From here, I already have two like terms, so that's usually what I take care of first. I have a plus 20i and minus 20i. Interestingly here, well, 20 minus 20 is 0. So since these have the same value with opposite signs, they actually cancel each other out. That goes to 0, so they basically go away. And here I'm left with 25 minus 16i squared. Now, I'm not done again because I have an I squared left, and I'm not going to ever have answers with I to an exponent in them because they can always be simplified. So I'm going to go one step further and replace the I squared with a negative 1. Negative 16 times negative 1 is positive 16. And you end up with 25 plus 16, which equals 41. Now you'll notice this is a pure real number. There is no imaginary component. The reason why is because the two binomials I asked you to multiply are what we call complex conjugates. Let me write that out. Complex for complex numbers, right? They have imaginary numbers involved. Right? And the conjugate basically tells me that they are opposite of each other. Okay, so if you look at them more closely, and I can erase this to make it more clear, you'll see that both sets of parentheses have the same two terms with the exception of the fact that it's an opposite sign. So we have 5 minus 4i, and we have 5 plus 4i. Okay, so when this happens, and it's the same terms with opposite signs, what's going to happen is the terms with I are always going to cancel each other out, right? Because you're getting those from these numbers being multiplied and these numbers being multiplied. So it's always going to be the same thing with opposite signs. If you have the same numbers with opposite signs, they're always going to cancel. So when you have complex conjugates, you will always get real solutions, purely real solutions. Okay, and we are almost done, and we are on to our last operation, which is division. Now, our instructions say to simplify the expression. Now, you cannot just outright divide 4 plus I by 2 minus I. There isn't a way to do it, but we can simplify this. When we say simplified, we want it in the most simple form, and we don't want any imaginary numbers in the denominator. So if there's still an I in the denominator, it's not simplified. Okay? Now, the way we simplify this is we actually multiply both the numerator and denominator of the expression by the complex conjugate of the denominator, right? Because our goal is to get the I out of the denominator. So remember we talked about complex conjugates on the very last slide, and we said complex conjugates are when you have the same terms but opposite sign. So instead of 2 minus I, I'm going to put 2 plus I. And I told you that when you multiply complex conjugates, you always end up with a purely real solution. So when I multiply 2 minus I times 2 plus I will get a real number in my denominator, and that's what I'm looking for. But I can't multiply the denominator by 2 plus I unless I also multiply the numerator by 2 plus I. And the reason is because if I multiply both the numerator and denominator by this, it stays equivalent, right? Because 2 plus I over 2 plus I, well, anything divided by itself is 1, okay? So I just have to multiply the numerator and denominator by the same thing as each other, okay? Now, sometimes it can help us to remember if I'm multiplying these terms by each other, I'm multiplying these entire quantities by each other, I'm just going to put them in parentheses to sort of help me visualize that, okay? And what you're doing with division is you're actually going to have to multiply out 2 sets of binomials every time you do one of these divisions. So just be aware that they're going to be a little bit more time consuming. But what I'm doing is basically the same. I'm still doing a double distribution. So I'm going to start with the numerator. I'm going to distribute 4 to 2 and 4 to I. And then I'm going to distribute I to 2 and I to I. Okay. And then I go ahead and I'm going to multiply those 2 binomials in the denominator. Again, I'm going to distribute 2 to 2 and I. And then I'm going to distribute a negative I to 2 and I. So that gives me negative 2I and negative I squared. Okay. Now, from this point forward, you're going to be doing multiple steps kind of each way. Like you're basically going to have to do the same thing in the numerator and denominator. So for both the numerator and the denominator, I'm going to sort of identify my like terms. So in the numerator, I have plus 4I and plus 2I. In the denominator, I have plus 2I and minus 2I. Okay. Again, and this is always going to happen in the denominator because that's the whole reason I multiplied by the complex conjugate. But those two are going to cancel each other out, right? 2I minus 2I is 0. Okay. It's not going to happen in the numerator. Okay. So I'm actually going to combine those. So we'll be left with 8 plus 6I plus I squared. And then in the denominator, we have 4 minus I squared. So at this point, I have gone ahead and I have combined all like terms. So now I'm going to go ahead and replace my I squareds with negative 1 because I know I can do that, and that'll help me simplify further. Okay. And when I do that in the numerator, I now have like terms again. I have 8 and I have negative 1, right? I wrote it as plus a negative 1 just because that's how I tend to replace it. But again, plus a negative is the same as a subtraction. So this just reads as 8 minus 1, which is 7. Okay. So I have 7 plus 6I in the numerator. In the denominator, I have 4 minus negative 1, which comes out to 5. And this is as simplified as this is going to get, okay? And so basically, from all that work, what we determined is that our original expression, 4 plus I divided by 2 minus I, that whole thing is equivalent to 7 plus 6I over 5. Still an expression that involves an imaginary number, but we have gotten the imaginary number out of the denominator, which was our goal. Okay, so we have one more example before this video is over. This is the very last slide, and I want you guys, once again, to try this. Remember that the way you approach a division is you multiply both the numerator and the denominator by the complex conjugate of the denominator. So go ahead and pause this video, try to solve that on your own, and then come back for the solution. Okay, so as we solve this, I'm going to work a little faster through this one since you already have an example. Okay, but basically, just like I said before you pause this, hopefully you're listening to me, is you're going to start by multiplying the numerator and denominator by the complex conjugate of the denominator. So again, the complex conjugate is where I have the same terms, 5 and I, except for I have the opposite sign. So this time I have 5 minus I. And again, I'm multiplying both the numerator and the denominator. It's been a long video. Both the numerator and the denominator by that. Okay, and then again, what I like to do is I like to go ahead and throw these into parentheses to remind me that I am multiplying those quantities by each other, so I'm going to have to perform some double distribution in here. I'm going to start in the numerator. I'm going to distribute the 3 to both the 5 and the negative I. 3 times 5 is 15. 3 times negative I is minus 3I. Then I'm going to distribute the negative I, again remember always distribute the negative, to the 5 and the negative I. Negative I times 5 is negative 5I. Negative I times negative I. A negative times a negative is a positive, and an I times an I is an I squared. Now, I do it all again with the denominator. I distribute the 5, leaves me with 25 minus 5I. I distribute the I. That leaves me with positive 5I, and then positive times a negative is a negative, and I squared. And now it is time to find the like terms. So, negative 3I and negative 5I are alike. Negative 5I and positive 5I are also alike, but again, those go to 0 because they have opposite signs. So those go away, don't have them anymore. I'm coloring extra because it's late and I'm tired and this video is really long. Anyways, when I combine the like terms from the numerator, I'm left with 15 minus 8I plus I squared. In the denominator, I have 25 minus I squared. Okay. At this point, there's no more like terms to combine, so it is time to replace I with negative 1. Sorry, I squared with negative 1. So I'm going to do that in both my numerator and the denominator. I'm going to take my I squareds and replace them with a negative 1. Now, you could also write this here. Instead of writing plus negative 1 like that, if you want to just write that as minus 1, you can. Just be really careful that you're only writing just minus 1 if you had a plus I squared, because like we'll see in this denominator, if you have a minus, you need to put the minus sign, and then you're replacing the I squared with a negative 1. You still really have to write it out separate, like a minus and negative. Okay. But yeah, now we're in the last step of this entire review lesson. We can combine 15 and negative 1 because those are both constants. 15 minus 1 is 14, and it leaves the negative 8I there because it's not combined with anything. 15 minus negative 1 is 6 because minus a negative is the same as a positive. And my answer to this very last problem is 14 minus 8I over 26. And that is now simplified, and our video is now done. So hopefully that was helpful. Hopefully you at this point feel like you've mastered all of this content. Just some reminders before I end the video. You do have an optional Delta Math review. It does not cover everything. It doesn't cover division that we just did, and it doesn't cover solving the equations. That is not because I didn't want to give you practice. It's because Delta Math does not have those skills, which is unfortunate but true. So make sure you are practicing those skills enough. You have to rewatch those portions of the video. If you have to go back to what we did those weeks, if you need to email and ask for extra help, extra practice problems, I am happy to do so. Just let me know. But yeah, make sure you have practiced plenty, that this is all second nature, because you are going to have to do all of these skills within the course of a quiz. And they shall be coming to you pretty quickly. So again, if you need help, please let me know. Sooner rather than later is better. And good luck in your studies.